Welcome back. We're going to be discussing the second part on our two-part series of free body diagrams.
Now, when it comes to free body diagram reactions, there's different types of support reactions. We can have a cable, rope, or chain that's supplying tension. I'm going to go ahead and make sure we put that. We can have a pin, we can have a roller, or we can have a built-in cantilever. To aid in completing free body diagrams, connections are often identified with letters. So in this case here, cable, rope, and chain replaced with a tension force only. Weight supported from a cable attached to a ceiling. So here we're going to be having tension force in here. Weight of object, they're using W. A lot of times, it really depends on what book you're reading. Sometimes they'll use W, and sometimes they'll use F sub W. A sign with weight W is hung by two cables as shown. Draw the free body diagram of the sign and cables. Well, I'm going to give you a few seconds here. Okay, hopefully you've drawn your own here to see how you're doing. If not, go ahead and pause this again and draw it. Put it up there in the problem section of our notes. Okay, here's what it's going to look like. So again, if you're not done, pause it. Free body diagram of signs and cables. Tension force in cable A. So on here we have a tension force in cable A. We have a tension force in cable B. And the one thing that wasn't on there was the W, the weight that was holding it down. Alright, so we had tension in both directions, the left and then up and to the right, and then the weight was pulling it down. So there was our tension. Alright, pin support replaced with two reaction forces, one vertical and one horizontal. So what we see here then, a pin. Here's a picture of a pin, and what this means is that it cannot move. It's not able to move like right, left, or up and down. It's pinned into place. So there is you could call it a normal force because it's pushing up, and then there's also a force right here in the X direction. Roller support, all right, with one reaction force. In this case, we have just a normal force. That's the only way. It's a roller because it can roll. This is used sometimes in bridges, suspension bridges or big bridges when they're going to heat up and cool off quite a bit throughout the course of the day, so that they have room to move. And the last one, the pin one, it's not able. There's a force right here, and that could be going to the left as well, but there's a force that's holding it in place. It's not allowing it to move to the left or to the right in the pin. So again, in the roller, this would be used in big bridges so that it can move with the heat and contraction and expansion of the parts of the bridge. Common support reactions. Beams and truss bridges are usually supported with one pin support and one roller support. This is called a simply supported object. Well, in this case, the left-hand side, over here on the left, we know that there's going to be a force that goes up, right, and it's a roller one. And it's at point A, and it's in the Y direction. So even though it says ray, there's a force, reactionary force. That's what the R stands for. The A means it's at point A, and Y means the direction. There's also going to be a force here, a reactionary force. It's at point A, and it's in the X direction. So we have rax and ray. On the right-hand side, all right, we only have one support force, or one reactionary force. It's at point B, and it's in the Y direction. So we have RBY. There isn't one in the X direction because this can roll. There's nothing keeping it from rolling at this point B. There's nothing keeping it from rolling at point B. Built-in support. All right, built-in support, a cantilever, replaced with two forces, one horizontal and one vertical in one moment. So whenever we have a cantilever, we're also going to have a moment. And notice in this case, our moment, especially with there being a force over here, all right, some type of load over here. There's some type of load. So it's wanting to go down. It's wanting to spin it, all right, in a clockwise direction. It's wanting to spin like this if it could pivot right there. So that means that our cantilever is providing this moment in the other direction. So it's not only keeping it from moving left and right, it's giving us this moment. So here we have this cantilever, and we've got to show all of these things. This cantilever is keeping it. It can't go right, it can't go left, because you could think of it as being glued into place. It can't go up and it can't go down because now it's locked into place here. It can't go down and it can't go up. The other thing that it's providing then is this moment. So what they've shown over here, again, it's got a force, a reactionary force, a normal force pushing up. That's at R, or it's a reactionary force. It's at point A. It's in the Y direction. We also then have a reactionary force at point A in the X direction. And then we have this moment, because this load is wanting this object to twist like this in this direction. So we have to have this moment, all right, this moment at point A that is counterclockwise. All right, summary support reactions. Whenever there's contact, all right, when there's contact between an object and whatever's holding it up, there's going to be a normal force, whether it's a cantilever, all right, or whether it's a pin or a roller. There's going to be a normal force. It's going to be in the Y direction. Cable, rope, and chain, we're going to always replace those with a tension force. We're always going to replace those with a tension force. Pin, we're going to replace with two reaction forces, one vertical and one horizontal, because it can't go up and down, and it can't go left and right. So here's our first one now that we're going to use two forces. A roller is only going to use one force. All right, it cannot go up and down. You're going to have the normal force here. I guess I shouldn't say normal. You could have a roller that's on the side of a building so that it could slide down or slide back up. So you wouldn't really have a normal. Well, you would, but not maybe the way that my students who haven't taken physics understand the term normal. Typically right now we've used normal just to mean up. But normal can mean up. If we're pushing up, that would be the normal. It's not really a normal force, but you could think of it as a normal force. That right there could also be a normal. It's the same concept. It's just normal is a very specific one, which means perpendicular, straight up and down. Or perpendicular, we won't say. You could think of that as normal. We'll keep it simple for you for right now. Oh, what I didn't talk about here then is this built-in cantilevers. All right, you're going to have two forces and a moment. All right, the moment's always going to be in the opposite direction that the object would twist according to the load that's being placed on it. Sometimes there would be a load that would be opposite of the one we just saw. All right. Okay, on here, I want you to pause this, and I want you to go ahead now and to draw in, make your own free body diagram on the second part of the notes, on the second part up there at the problems. If you've already used that, then use a different part of the notes page. And I want you to go ahead and pause this now and draw your own free body diagram for this truss bridge. Okay, as I see this now, I've got two spots here. In both cases now, I'm going to have some type of normal. So I have a reactionary force at C in the Y direction. I have a reactionary force at point A in the Y direction. The other one we're going to have now, because this is a roller, so there's only one force acting here, and that's perpendicular to it, is over here at point A. Because it is a pin, I'm also going to have a force in the X direction. That's a reactionary force at point A in the X direction. Well, hey, I hope this has been good for you. We'll be working quite a bit here now with some free body diagrams as we work towards being able to do more than just build the bridges. We want to be able to calculate the forces that are being exerted on the bridge. I'll catch you on the flip side.